Um, I think we are good now. Okay. Okay, let's start it. Good morning, everyone. Welcome to the 2025 Spring Webinar hosted by the NCME Scaling, Linking, and Equating SIGME. Thank you for joining us. My name is Min Wang, and I'm the chair of SLE SIGME. Together with me today from our leadership team are Sung-hee Park, Tan Kim, and Jinhua is on the way, I think. SLE SIGME usually put together 2 webinars or training sessions every year. If you'd like to receive the information for our future events, you can join our SIGME to add to our mailing list. This is very easy and totally free, covered by your NCME membership. We'll put the instruction later in the chat box. Okay, today we are very excited to have Dr. Tom Benton and Dr. Matthew Carroll from the Research Division at Cambridge University Price and Assessment to share their research work, the biggest equating study in the world ever, double quote, which testing equating method works best. Before we get started, I'd like to give you an introduction of our 2 guest speakers. Dr. Tom Benton completed a PhD in statistics at Imperial College London in 2002 and has worked in educational statistics ever since. For 10 years, he worked as a statistician for the National Foundation for Education Research, NFER. Since 2012, he has worked as a principal researcher for Cambridge University Price and Assessment, with a focus on the psychometric aspects of test delivery, such as equating. Dr. Matthew Carroll is a senior researcher at Cambridge University Price and Assessment and has worked there for 8 years. His work focuses on statistical analysis of large educational datasets in areas such as automated text analysis, malpractice detection, and impacts of the COVID-19 pandemic. Prior to working in education research, he studied science at the University of Cambridge, completed a PhD at the University of York, and worked as a research scientist. Okay, we are very glad to bring this talk to the SLE community and hope this can inspire follow-up discussion and collaboration. During the presentation, if you have any questions or comments, please ask them in the chat box. We will have a Q&A in the end. With that, Tom and Matthew, thank you for being here today. Looking forward to your presentation.
Thank you very much. So we're going to talk today about equating. The title of our study is actually inspired by a compilation album that was released in the UK in the 90s called The Best Album in the World, ... ever, exclamation marks. That inspired our title of this study. And Matthew will talk in a minute about why we think this equating. So what makes it big? We'll talk about that in a second. Just to introduce us a little bit, our organisation is part of the University of Cambridge, technically a non-teaching department. And we've run a lot of exams, lots of different types of exams for a long time. What we're really going to be focusing on today, the source of the data for this presentation, is about high stakes exams taken by mainly by students of high school age. We in the research division take a lot of research to support the delivery of these assessments. And one thing that's really important in all of these assessments is comparability. So if 2 people have taken different exams in the same subject, perhaps in different places or at different times, then they want to be able to interpret their grades the same way. So equating is a really important part of that. And in our context, we have a very high volume of exams, not just one exam being taken by lots and lots of people, but many, many, many different assessments all being taken within a very short space of time. So what we're really looking for when we do these kinds of studies is to identify a small number of the best equating techniques that will help us in our kind of high assessment volume environment that we work in. So to talk more about the study itself and its background, I'll let Matthew take over.
Right, thank you, Tom, and thank you all. Thank you for having us today. So My role in this is to give you a bit of background to the study and also take you through the methods and through our high-level findings. And then I'm going to pass back to Tom, who's going to take you through some of the more detailed findings. So to begin with, we'll set the scene. I'm sure for this audience, I don't really need to describe test equating in detail, but just so that we're on the same page here, equating is useful when we need to say that results from two or more tests are equivalent to one another. This could be because we're using different test forms in the same session, perhaps for security purposes. It could be like a tiered assessment where lower attaining candidates take one test form and higher attaining candidates take another. It could be tests in different sessions where we need to make sure that our grades are comparable over time. But obviously this is challenging because, as we know, test difficulty can vary and student ability can vary. So it's not always easy to say that any two scores are exactly the same. And equating is just the statistical process of aligning scores from different tests so that we can report them on the same scale. We're looking at the question which scores on each form are equivalent to one another. Whoops, here we go. Thank you, Tom. Now, in our team, we tend to use the textbook by Colin and Brennan, Test Equating, Scaling and Linking, as like our authority on equating procedures. And so following their terminology, today we're thinking about the non-equivalent anchor test design. That means that we've got non-equivalent groups of students taking our different forms. They might differ in ability. That makes things a little more difficult. And to link our forms, we've got some items in common between them. These are common items or anchor items, and that's what's going to allow us to create the statistical link. And Colin and Brennan described various methods through which we can do this, both in classical test theory paradigm and in the RASH or IRT paradigm. There are, however, a lot of methods, and it's not necessarily clear which method under which circumstances is best. There are studies out there making comparisons, but they might only compare a few different methods at a time. Evaluations of the different methods might use a small number of real data sets or simulated data, which might not always behave in the same way as real data. And what this means is that, as Tom said, in our instance, we're trying to do this in practice, and the methods might not perform as well as expected or as well as advertised. So we carried out this study to effectively try and do the biggest ever evaluation of equating methods using real data. We wanted to find out what works in practice using real data. So just to give you an insight into the study data, I mean, as Tom has indicated already, we're in a good position to do this because our organization holds a lot of item level data from tests administered all around the world from a range of qualifications. Some of the test names that you might have heard of, the qualification names are GCSE or IGCSE, A-level, O-level. These are taken literally all over the world. Our assessments may differ from some that you are kind of familiar with. I've got an example here. This is from a real test. This is a geography test. We've got a mixture of dichotomous and polytomous items. We've got some short responses, maybe some multiple choice responses, and some longer responses. So we've got quite diverse item types and item tariffs within the same test. And we hold a lot of this data. So to do our study, we sampled 1,000 of these real tests at random from our whole stock of test data. With some conditions on inclusion, we wanted at least 5,000 candidates, at least 15 items, and no optional items. And this meant that we were going to have enough data to actually work with when we came to do our equating. The resulting data, this 1,000 sampled tests, covered 10 different qualification types, 40 subjects, and all the way from 2009 up to 2023, when we actually did the work. The reason I emphasize this is because we've got a really diverse, large data set here that we're working with of real test data taken by real candidates. The idea was that we would then loop through these 1,000 tests in turn, and we were going to turn them into pseudo tests and equate the pseudo tests created from our real tests. So let's just talk you through the process that we used for this. we started with item level data just from one test. This is, I should say, completely made up data. This is a random number in Excel, but it shows you kind of what we're doing. We've got candidates on our rows and we've got the different items in the test on our columns. So we start with our single test. And then the first step was to identify what we'll call our split item. And this was the item that came closest to producing a 50-50 split in candidates based on its on performance on it. So here we see item 10, half of our candidates got it right, half got it wrong. And so we're going to use that to create two different groups, group 1 and group 2. We're then going to discard that item. It plays no further role in our simulation. We then select items to form an anchor test. And this is completely at random, only done to hit a particular length. And the length of the anchor is one of the conditions we controlled. So we select items at random to achieve a total number of marks on our anchor test. Here we've got item 4, 11, and 14 in our anchor. We then divide the rest of the items into two different forms, form X and form Y. Again, this is at random. So form X here is all of those in purple with the anchor, and form Y is all of those in green with the anchor. And I should just be clear here, this was again done at random. We're trying to get approximately equal marks in each form. We didn't control the relative difficulty of the forms themselves or the anchors. But what we end up with is these two pseudo tests from one test. We then use the scores from all candidates who took the test on both of these forms, which are effectively just a subset of the items, to estimate the true relationship between our two forms using equipercentile equating. So this gives us our true relationship. We then go back to the groups we defined earlier, and we sample those to create our sample of candidates taking each form. This is going to be with a chosen level of ability difference and of a chosen sample size. So just to talk about the ability difference, we could do it purely deterministically based on the group we defined earlier. If we take that group we defined earlier, that grouping based on the split item, one group is going to, on average, be higher performers, and one group is going to be lower performers. So that leads to a fairly large ability difference. Equally, we could do it completely at random, and that leads to two groups with no structural ability difference. We could also do a mixture of the two. The other thing we can control is how many students we sample for each of these groups. We sampled anything from 50 per form up to 2,000 per form. So those are our kind of simulation conditions that we controlled. Once we've got our sample of students taking each form, we look at their scores on the anchor test, the scores that they achieved on the actual items, and we use those to carry out a range of equating techniques, and we retain the equating functions. We then evaluate the equating functions against our source of truth that we derived earlier. The main metric that we do this with is the mean absolute error. So we see on this graph, we get, we compare our true relationship, which is here in blue, to the one we got from our equating technique. We look at simply the absolute difference. We're not going to take into account the sign of the difference, just how far away from truth it was. And we take the average over the range of scores on the form, and we're going to weight that as well by the number of candidates that achieved each score, which means that we're going to pay more attention effectively to the scores that are typically achieved. We don't want our method to be kind of swayed too much if the very tail of the score is a way off, but nobody achieved that score. That's going to be down-weighted in our final calculation. So what this does is it gives us one value for each method, for each data set, and the larger the value, the further away from truth it is, the more error. I should just point out as well, we did look at root mean square error and bias, but today our main source of evaluation here is going to be the mean absolute error. So just to kind of really quickly run through, just so you understand the scale of this, the scope of this, we sampled 1,000 real tests, which ranged anything from 15 up to 67 items, with maximum scores of anything from 29 up to 140. This led to 2,000 pseudo tests being generated, ranging from 6 to 42 items each, and with scores of 15 to 86. I should add that our mean scores here, we've got a range of means for our pseudo tests and our anchors. That's because one of our conditions was anchor length, which means that depending on the condition, our mean number of items and our mean anchor length differed. And 1,000 anchors generated, again, ranging from 2 to 17 items and a maximum score of 3 to 35. Just to review our simulation conditions, we could select either a tenth, a seventh, a fifth, or a quarter of the total marks on the original form as our anchor. This equates to about 18% up to 40% of the form marks, the pseudo test marks. We could control the group ability difference. This could be purely deterministic based on that performance on that splitting item. It could be purely random, or it could be a mixture of the two. This is going to lead to a maximum difference, virtually no difference, and a medium difference in ability between our groups. We could control the sample size, ranging from 50 to 2,000 students per form. What this leads to is 60 different combinations in total. We then applied over 50 equating methods or variants of methods. So we've got those based on RASH, IRT, classical test theory. This led to over 3 million equating operations in total. And this is why we think it's one of, if not the biggest equating studies ever. I'm not going to linger on this slide. This is just so that you can see the range of methods we tried. We did everything from RASH with the partial credit model through to more complex IRT models, graded response and generalized partial credit models. We looked at some classical methods, things like frequency estimation, equipercentile, chained equipercentile, linear, mean, circle arc, and then there were variants of these as well. This isn't everything. We explored some extra methods, which Tom's going to talk to you about shortly. And I should be clear, all of these were applied in R software, particularly the Equate package, MERT, TAM, and Dexter, and then some internal packages as well. So that's our methods very quickly. And now I'm going to very briefly run through our kind of high-level findings before passing to Tom, who will take you through some more in-depth findings. So first of all, let's just look at the impact of the different simulation conditions on our results. These plots have our mean absolute error up the y-axis. So the further up the y-axis we are, the further away from truth our method was. And our x-axis has our different anchor lengths. And then within the clusters, we've got different group differences. And then our plots are different sample sizes. So what we found was basically what we hoped to see, which was that we've got bigger error was associated with, first of all, larger ability differences. So for that, we can look within the clusters of the box plots. We've got the random grouping on the right, and then we've got the maximum group difference on the left. And what we see is, as might be expected, it becomes harder to equate the tests when we've got more different groups. This is to be expected. We get more error with the maximum group difference condition. We also see greater error when we've got shorter anchors. And so to do that, we compare our clusters of boxes within our plots, and we'll see that the level of error kind of increases. It's not a huge increase, but going from, say, 40% of marks to only 18%, we do see an increase in the error associated with that. As we might expect, more shared items leads to better equating. And then smaller sample sizes led to greater error as well. So we can compare across the plots here, going from 2,000 students per form on the right over to just 50 students per form on the left. Again, this is what we'd expect. So this is kind of reassuring. It suggests that our simulation is working because the conditions have the expected effects on equating error. It also sets the scene for the findings we're about to discuss. So let's look next at which methods worked best. How do the methods compare to one another? Now, this plot has kind of rotated our axes. So now we've got the error going up the x-axis. So the further to the right we are, the more error there was. And we're just going to look within a particular condition now. This is with a sample size of 1,000 per form. This is with random grouping and 25% form overlap, so kind of somewhere in the middle. And what we see is with the random grouping, most methods were pretty similar. What we do see is the identity equating, so simply saying, 1 mark is equivalent to 1 mark, 10 is equivalent to 10, and so on. That was worse than the others, as we might expect. It's certainly more variable. But generally, the methods were all pretty similar. And that's kind of what we would hope to see. If there's no meaningful difference, if we've got equivalent groups, then the various different methods actually perform really quite similarly to one another. If we change now to the maximum group difference condition, but again with sample size of 1,000 and an overlap of 25%, we see more differentiation between those methods. So I'll just pick out a few highlights from what we saw. We see that several of the classical methods performed similar to or worse than identity now. So that particularly we've got some circle arc variance, some mean variance, some linear variance, and frequency estimation equipercentile. They're all as bad, if not worse, than identity when we've got this maximum group difference. RASH and IRT methods maintain their performance much better when we've got that large group difference. So we see in the first blue box, we see the more complex IRT models, and then in the lower blue box, we see the partial credit models, so those kind of RASH models. Interestingly as well, and I'm going to flag this because Tom's going to pick up this thread shortly, one thing we did notice was that a couple of circle arc variants perform surprisingly well to us, bearing in mind that there's a sample size of 1,000 here. It's a small sample method, but it was still performing quite well. We're going to pick that thread up shortly. But once again, many of these methods are broadly similar. We're not seeing too many of them perform terribly, which is kind of reassuring in itself. Now, if we look at what happens when we've got a really small sample size, so only 50 students perform, we start to see much greater error overall. What we do see, though, is we really get the best performance from these circle arc methods. Of the kind of complex IRT models, well, they did perform somewhat worse when we've got a small sample, as we might expect. And the partial credit model, especially that, fitted using joint maximum likelihood, maintained performance a lot better than the more complex IRT models at this sample size. But once again, many of those methods are still broadly similar. We're not seeing many completely fall apart. So let's cut to the chase. Let's look at the single best method for each combination. So this is simply across our 1,000 data sets, which method had the lowest mean of the mean absolute error values across the 1,000. Of course, there are other ways we could look at this, but this is just the lowest mean. We're going to focus on the 25% overlap condition because the others were quite similar. But I want to highlight two key patterns in the best results here. So first of all, what we see is that we see a big effect of group differences. So for that, we can look at our different rows. If we've got no difference between our groups, the classical test theory methods dominate. So we see circle arc, linear equating, chained equipercentile, and frequency estimation equipercentile. If, however, we have a medium or a maximum difference, that's where we start to see the partial credit model or more complex IRT models start to come in. So group difference has a real impact on whether we should be using classical test theory methods or IRT and RASH. The other thing we were seeing is this effect of sample size. So if we look at a sample size of just 50, perhaps unsurprisingly, circle arc kind of wins in every condition. This is unsurprising because circle arc is designed for small samples. When we move up to a sample size of 100, we start to see the partial credit model, particularly fitted with joint maximum likelihood and using true score. That seems to work best when we've got 100 with a group difference, and linear equating works best when we've got 100 candidates with no group difference. When we get larger still, that's when our IRT models start to dominate, the graded response model and the generalized partial credit model, although these were virtually interchangeable. These were fitted with concurrent estimation, so putting all of our data from both forms into the same model. And then when we've got no group difference, we see chained equipercentile or frequency estimation equipercentile at those larger sample sizes. So group difference and sample size seem to be the real driving factors for which method performed best. And for my final slide, I'll just kind of show you, this is just to illustrate how that best method changes with sample size. So here, again, we've got our error on the y-axis. We've got sample size on the x-axis. I should say this isn't kind of scaled. This is spread out evenly, even though our sample sizes are not kind of spaced in place here. So just for visibility, we've spread them out. At 50, the smallest sample, circle arc in red is just about better than partial credit model. Our blue, more complex IRT model is clearly a bit worse. As we get up to 100, partial credit model and circle arc are quite similar, but partial credit model is just about better. Still a lot of error in our generalized partial credit model. As we get larger, still the generalized partial credit model just kind of gets better and better, and the partial credit model and circle arc stay about the same. So this is the kind of pattern we're seeing. Those are our high-level results. And the thing is, we've got a lot of data from these simulations here. And so we looked at this and we thought there are many, many more questions we can answer with this. And so with that, I'm going to pass to Tom, who's going to explore some of those questions that we went on to answer.
Okay, I'm going to start with just by looking at choices we have to make between different IRT models in terms of how we fit them and how we use the results to do equating. I should say a lot of results will be very small, but we can find clear recommendations for doing one thing rather than another. And in order to do this, I'm going to look at distributions of the differences in mean absolute error between pairs of techniques. So this just reiterates this difference between partial credit model and more complex IRT, graded response model. What I've got here is charts where every panel is a particular amount of overlap between anchors and a particular level of group difference, and every point within a panel relates to a sample size. And I'm comparing each of these charts, so I'm going to be comparing two different methods here. It's partial credit model versus graded response model, okay? And simple interpretation is the point is below 0. That means the partial credit model is better. If it's above 0, it means graded response model is better. And one of the things you can see from this, and the reason to do it as differences, is just to note the scale on the y-axis here, which is about the difference in mean absolute error between the two techniques. And you'll note the scale here. This is like as a percentage of the maximum mark available on the assessment. It's only going from -4 to +4. We've got a very small scale here that we're reporting everything on. So what that tells us is a lot of the variation in performance is actually between scenarios where one method does bad. That often means all the other methods do bad as well, because it'll just mean we're in a scenario where something tricky has happened within the simulation, where performance on the anchor test happens not to reflect differences in the abilities of the candidates taking the forms as a whole. So a lot of these differences are very small. I'll show other results like this in a minute. For a moment, this just reiterates what Matthew was saying. So sort of smaller sample sizes, partial credit model doing better. To get to 500, it's very difficult to pick between that and other IRT, and then at larger sample sizes, the graded response model coming better. One thing I want to talk about is there's a lot of cases where we can compare two methods, and we've got all our scenarios. If we think about each point within each panel as a scenario, we've got 60 scenarios, and there are lots of cases where when we compare two methods, one method is always better than another, and we call that, I'm going to call that being dominated by another method. So this is just one example. This is where we're using graded response model estimated with concurrent MML estimation. I should say, to be clear, this is a multiple group concurrent MML estimation. And every single time when I compare true and observed equating, true would be better if we were below 0, observed would be better if we were above 0. Every single time, every single scenario, observed score equating does better on average. You can note this is by a tiny, tiny amount. Like the differences on the y-axis are fractions of a percent difference in terms of performance, but always consistently better. So if we do have to pick one method rather than another, we're using a complex IRT, we want to use observed score equating. For those who don't know, that means using the IRT to generate what would the score distributions be like in a common in a common population, and then using that to allow you to equate the two, rather than true score equating, which means find scores that are the two scores are equivalent if they are both the expected score from a particular level of ability. So that's one example, and it's just showing you one example of a method being dominated by another. There were lots and lots of these we found. So observed score equating, if we just talk about graded response model and generalized partial credit model for a moment, observed score equating always dominated true score equating. Using a two-parameter model, by which I mean not having a third guessing parameter for dichotomous items, that always was dominated. Two-parameter always dominated three-parameter. Interestingly, we've got these methods for if we do two separate estimations and then trying to align two sets of IRT parameters to allow equating. Two ways of doing that: Stocking-Lord method or the Hay-Barrow method. Stocking-Lord method always did better. Always in all of these things, it's by a tiny, tiny amount, but it happened every time. Multiple group concurrent estimation dominated all methods of separate estimation as long as our sample size was bigger than 500. So if you're using complex IRT, observed score equating, two-parameter model, and then concurrent estimation is best. Similar findings for the partial credit model, but one thing that was different and was the other way around was that when we're doing a partial credit model, we've said before, JML, joint maximum likelihood, dominated conditional and marginal maximum likelihood, should say that could be to do with the defaults for the way different software packages determine convergence. It's possible there's that, but if you just come in, use an IRT package out of the box, JML does better. But the thing that's different from GRM is for Rasch model, true score equating dominates observed score equating. So if we want to use a Rasch model, we want JML and we want true score equating, and again, put everything concurrently into the one model. Another thing I can look at, so I've got all this data, is what happens if our data shows the IRT model doesn't fit very well. And the way I'm going to do this is just split our various 1,000 data sets by how well does an IRT model fit the data, the overall data in that case. And I could have used lots of IRT fit statistics. Just for brevity today, I'm going to focus on one, the standardized root mean square residual, or SR-MSR. Because that's a mouthful, for the next few minutes, whenever I say the word misfit, I just mean standardized root mean square residual, okay? And the misfit statistic I'm using is about the amount of difference between correlations we see between items within a data set and the correlations we'd expect if that IRT model was really correct. And according to the literature, values of misfit below 0.05 imply a well-fitting IRT model. So let's see how that works out, this relationship between misfit and how well IRT does. So I'm just going to look at a few panels of the scenarios here just to give you an idea. So again, I'm looking at the difference between two techniques. Here, the difference between the graded response model in terms of its mean absolute error and the mean absolute error of chained equipercentile equating. I've chosen chained equipercentile equating as a kind of easy default classical method that we might be tempted to use if we're concerned about the fit of our IRT model. And here I've got two lines in each case, one for all those data sets where the IRT model was well fitting, that is, misfit was below 0.05, and the blue lines and with triangles on for wherever misfit was higher, where it was bigger than 0.05, although in this case they were always less than 0.1. And we can see here, particularly if we look along that top line where we've got maximum group differences, remember that's where we expect IRT to be the best, we've got big differences between the groups doing the different forms. Even when we have less well-fitting IRT models, they still outperform chained equipercentile as an equating method. So it tells us that even with things that are not fitting so well as we'd hope, using IRT still is a really helpful form of equating if we have big differences between groups. And this is the same idea again, but this time focusing on the Rasch partial credit model. I should say for this, there were very few instances where misfit was below 0.05 when we're using the Rasch model, obviously a much simpler model. And there were a few, but not that many, where misfit was above 0.1. Okay, so there are very few. The vast majority of our data sets had misfit between 0.05 and 0.1. So not brilliantly fitting, but not terrible. And again, this is just to reiterate, look at that top line where we've got big differences between the groups taking the different forms. Even though our IRT model, our Rasch model, doesn't fit perfectly, you can still see it working well in terms of outperforming the kind of default classical method that we might use. So kind of a conclusion from this is if we can get misfit below 0.1, that might be a sufficient check that IRT is worth using in those cases where we've got big group differences. Just going to finish off. After we'd had our first main run, we did have a supplemental run for two reasons. One, because in doing 60,000 replications of every method, we did identify bugs and wanted to rerun. That's not going to affect the results too much. I'm not going to talk about them very much. The thing I do want to talk about is that we noted how well CircleArc had done in our first run and wanted to see, is there anything that could pick up the kind of rationale of CircleArc equating, or take inspiration from it and develop some new methods that work along the same lines. And the reason to do this is that CircleArc equating in practice for us has had some rare issues in that in extreme examples it can become non-monotonic. So higher scores on one test equating to lower scores on another, which can be a problem. So in terms of taking the principles of CircleArc equating, this means having 0 mapped as a score of 0 on one test mapped to 0 on another, the maximum score in one form to another, and the mean mapped to the mean. And when I say the means, obviously that will be within the kind of predicted mean within the same synthetic population. And we're going to have those three points that map to each other, and we're going to put a smooth curve through them. That's the idea of CircleArc, and we want methods that do the same thing, but a slightly different way. One alternative is called odds transform equating, which I'll show on the next slide. And another which didn't quite do what I'm saying above, but was similar, was to just apply transformation to our scores before applying linear equating. Here's some more details on those. So this is the formula for odds transform equating. If you want to use it, I'm sure it'll be in the recording, or you may want to take a screenshot now. I'm not going to talk through the formula, but the thing I just want to talk about is you end up with a chart like this. So this is an example where we want to map 0 to 0, maximum to maximum, and the mean of 60 to a mean of 55, and we just get a smooth curve that goes through all of those. These curves will look very similar to what you would get from CircleArc, except in extreme circumstances. One thing that's different about odds transform is it can be extended by adding an extra parameter k here. Again, if you're interested, do take a screenshot, feel free. So we've got an extra parameter k here with a particular formula to define it here. And what this allows is to set the gradient at the mean points that we're mapping to, set the gradient slope there to be determined by the ratio of the standard deviations. This will mean that at these points, after the equating function, it will be very like linear equating, but it will still nicely, and smoothly move towards 0, 0, and maximum, maximum at either end. In order to use odds transform equating, obviously the two test forms we're equating are taken by different sets of candidates. That's the whole point. And we need to estimate that mean and possibly the standard deviation in a common population. And to do this, we could use any of the same approaches that we've used for that in CircleArc equating. So Tucker method, Levine method, nominal weights method, you can have any of those in existing literature. And in fact, we could use a chained method versus odds transform equating as well. That also works. The other new method was transform linear equating, which all we do is we apply the transformation down here to the scores on form X, form Y, and the anchor, perform linear equating, and then transform everything back And this transformation was chosen because it is very similar to an arc sign transformation that was chosen that stabilizes conditional standard error of measurement suggested by Coulomb, 1988. So the blue line here, blue solid line, is Coulomb's transformation. The dashed line is the arc sign, sorry, the arctan, hyperbolic arctan transformation, and they're very similar. So we can just make this transformation regular linear equating, transform everything back. And the arctan one is preferable because it's easier to invert at the other end. So these are results, just a few results of this supplemental run. What I want you to do is just focus firstly on the circle arc, just the 2 points on the left-hand side of each chart, the red and the grey. The red is circle arc, the grey is odds transform. That's the basic odds transform. And if you squint very hard at this chart, you can see in every case, the odds transform method is ever so slightly better than circle arc. So it gives us a nice alternative to circle arc equating. Other clear finding, if you now focus on the right-hand side of each set of points, we're comparing linear equating and transformed linear equating. So this is still linear equating, but just with that transformation before and after we talked about. And again, we can see that in every case, applying the transformation makes the linear equating more accurate all the way along. So that's two clear findings. Odds transform very slightly better than circle arc. Transform linear very slightly better than linear. Final method was this extended odds transform method that I've got in the middle in the blue. Results here are a little more complicated. There was a kind of clear the answer of when to use it, when not to. It depends on many factors. You can see that we've got huge group differences. It never won. In this case, if you've got medium-sized group differences, sometimes it would be the best method. But that's going to be a topic of articulating when it's the best. It's going to be a topic for further research. If we go back to this idea of dominated, there are lots of classical methods that are dominated, and it's worth doing this after having added in these extra methods. So things that you shouldn't do if you're only interested in accuracy and you've got sample sizes between 50 and 2000, never do identity equating. It's dominated by loads of other things. Never do mean equating. Circle arc or odds transform is always better. Never do circle arc. Odds transform is better. Never do linear equating because it's better if you've got a transformation on it. And never do unsmooth decremental equating because it's always better to put some smoothing on it. That's, of course, assuming that the only thing you care about is accuracy. Obviously, in practice, there can be other factors, such as how easy it is to explain what you've done. So, final slide. At the end of all this, we wanted to boil down all our results into some simple recommendations. Come on, which methods do we think we actually need in our toolkit to do equating and under which circumstances? So to do this, we summarized everything down into just two group differences, big differences, where the two groups are more than half a standard deviation apart, and small differences where they're less than half a standard deviation apart. This would be our maximum group difference and our random group difference, and our median one kind of sits in the middle of the two. And sample size is obviously going to make a difference. So small sample sizes, odds transform methods. Bigger sample sizes, then if you've got a big group difference as well, IRT. If you've got a small group difference, transform linear equating, maybe rash equating, depending if you've got something, approaching half a standard deviations difference in ability between the groups. And then with big sample sizes, not much difference between groups, equipercentile equating is the way to go. There is some subjective judgment in this final choice of 6, slightly thinking about ease of implementation as well as accuracy. There are some limitations. Clearly, this isn't going to be the final word on equating methodology. We haven't done very small sample sizes, very large. We haven't done every different type of test. And we haven't thoroughly explored differences in, for example, the difference between two forms, although the little bit of sensitivity analysis we did around this didn't really change our conclusions. And we haven't reviewed every possible method. Like I said at the beginning, this title of this study was inspired by an album called The Best Album in the World, ... ever. Well, within 1 year, there was The Best Album in the World Ever, Volume 2. And in the same way, this is the biggest equating study in the world ever. so far. So we'll be very happy to hear suggestions for what further research needs doing, or of course, any questions. And I'm happy to listen to those now.
Well done. So sounds like we should have more events planned. And also, like I noticed a lot of art packages used in your study. So maybe we can talk about like a training session for our community in the forward.
Sure enough.
Let, so let me kick off the open discussion. I know all of our audience must have a lot of questions. And just hold on that. You put in chat, and I highly encourage you to speak up and open your video, if possible, a camera. So Dr. Neil Dorrance cannot join this meeting. However, he read the abstract and feel it's very interesting study, and he recommend two studies. I'll put in the chat. And for the authors, but also for all the audience. Let me see. So one is a study done by Dr. Sihari and Holland. I hope I read the name correctly. The primary takeaway from this work is it employed different approaches to simulating data. Is that the linking method that most attuned to the assumptions underlying the generation of simulated data is the one that should win a battle of the method. Okay. And then Dr. Dorrance has a commentary set this study and other work, and it includes a summary of this work and close with a note about how to make inferences from simulation study to real data applications. So hopefully this can help your future work if you haven't read on that. And then another one is a question from Li Liang from the Center of Educational Measurement and Assessment at the University of Sydney. Cannot join because of the time zone issue, but Dr. Li Liang want to say thumbs up to Tom and Matthew. This is really a historical superground experimental research. I'd like to contribute a question to the discussion. What if none of these 50 methods work perfectly as expected to meet the current testing demands when we aim to serve very high-stake testing for college admission?
Sure. Okay. So if none of them work perfectly, that is not something we talk about. It definitely happens. So in our study, I did definitely see instances where, well, at least, you've got the big difference between groups. And the biggest problem you could have, you've got a big difference between groups. You need to run an IRT model, but the IRT model does not converge. Okay, so that was the biggest issue where we could get, the worst results. That's where that would happen. So there was some uncertainty over the parameters. I think in every case we looked at, certainly in those cases, you would see that happening, and you would be able to pick something simpler that you would at least be able to feel comfortable with. And the other thing to say in that situation is this is where I feel really simple methods like circle arc, like odds transform come in, where you have a complicated method, you're not sure it's working, and you need to have a simple alternative where you can convince people, here's something explicable that we can do. We know it's not, it's perhaps not our first choice, but it's going to give you a sensible set of results in that situation. So, moving towards simpler approach is important. And I would also say this is not from our study so much as from life in operational settings, always cross-validating against other sources of evidence, particularly, and just have people look at the exam papers. Is what you're coming out with, does it look reasonable? I'm always having that kind of human check on that is important as well. Do you have anything to add, Matthew?
I would just emphasize that, I mean, in the most challenging conditions that we simulated, so a very small sample, 50 students perform with maximum group difference. We did see some reasonably large errors. But I mean, particularly when we've got virtually equivalent groups, or where we've got even the medium group difference condition. And particularly when we get into larger sample sizes, the levels of error against truth did really come down, and most methods were quite similar to one another. So although, I mean, there's a question about whether any method can truly work perfectly. In our study, we could, I suppose, attribute perfection to having a mean absolute error of 0. Obviously, in real usage, we don't know what truth is. But what we can say from this is that in those more amenable conditions, many of the methods were actually pretty good. And certainly the kind of summary that Tom gives of almost like the range of best methods to consider, that allows us to, you could try a few of those and just see what degree of variation there is, without having to feel like you need to try 10 or 20 or 50 or more. So actually it's kind of quite encouraging, as far as I would see it.
Okay, we have some questions added in the chat. Again, I highly encourage you talk, like with camera open. We would like to see your face. But if not camera ready to play, feel free to drop in the chat. So number one question, can you talk about how the various methods affect decision consistency?
Yeah, that's fairly straightforward. So a lot of the differences in the methods we are talking about, when we use them in practice, there would mainly be a difference of 1 score point, especially when we've got larger, when you're talking about small differences. So in terms of how it affects decision consistency, that will basically depend on how many people you have dead on each mark point. So it will make that much difference to decision consistency. It's sometimes better actually in terms of doing a methodology study just to think in terms of mark differences, because otherwise you're kind of always going to, once you start rounding it to actual cut scores or something like that, you're always going to produce large differences, and you maybe wouldn't be able to see some of this small methodological improvement that you can get.
I think I missed a couple of questions. What's the first one?
I can see a question about methods being dominated by others. What is dominated by? It means simply that you could do something else that's better. That's what it means in this context.
Well, I think just to be really clear, it meant that under every simulation condition, another method performed better than it. So there was always, under every condition that we trialed, a particular method outperformed it. So effectively, that would mean that there would be no benefit of choosing the worst performing one, because there was always something.
Yeah,
better.
so an example is if you've chosen to do mean equating, very simple method, just add on an amount for the difference in means. It is always better to do something different. It's always, doing circle arc equating would always be better than doing mean equating. That's the kind of thing that it meant.
I'm aware there were two questions earlier in the chat.
Yeah, go ahead.
There's one which Tom may need to take, about well, your discussion of the more detailed results, whether we could take an experimental design approach to understanding some of the effects.
We could partially. So some of it is within experimental control. Anchor length, the things we talked about, anchor length, sample size. What was the other one? Group difference. That's within our experimental design, so we can search things in there. Other things that are interesting, like IRT fit and things like actual ankle length, physical ankle length, not just in terms of proportion overlap, but how long is the whole test, for example. Those kinds of things are not under control. They just come out within the data sets. It would be possible to throw all that into some kind of model. I don't think I would find anything different from what I've already got. I suppose you could find some more nuanced ones. And I think we've kind of focused on where we've got a really clear, like this method dominates that one. This always happens. But sure, you might be able to find some more nuanced ones. But we had so much to write about anyway. I didn't feel the need to do it, but you sure could do that.
I also think, just to emphasize, one of the as we set out, one of the real kind of driving factors behind doing this was to use real data, which obviously to some extent limits our ability to control some of these things. And then we get back into the discussion about simulations versus real data. So there are definitely ways it could be done, but I think within the framework we tried to work in, we were limited to just what we could do with the real data. There was another question earlier as well, which is about anything that we were surprised at compared to Colin and Brennan's book and previous equating studies. Tom, you're probably best placed for this one.
Was there anything was?
I've got one, if that helps.
Oh, go ahead.
Well, for me, I think for both of us really, it was actually the widespread successive circle arc. To the extent where we looked at our initial results, you know, our computers had been churning away for days and weeks, and we got the results out. And circle arc, we expected it to do well in our small sample, but it was the fact that it actually did consistently well, even at large samples. It suggested a much kind of wider utility for it that we hadn't necessarily been expecting. I mean, it wasn't the best at the large sample sizes, but it was usually up in the top few methods. And obviously, that was the thing that inspired Tom to go on to develop the odds transform method. So I think, at least in the initial simulation run, the success of circle arc was probably what surprised us.
Okay, I think Jinhua have a question.
All right, thank you, Ming. So first of all, I want to thank both presenters, and I'm really glad we get this presentation from UK, and that's one of the purpose of Sigma, SIGME, to invite the different perspectives. So really well done. Thank you both. Back to the study itself, I guess my biggest concern or question is related to the anchor, the content representativeness of anchor. There are tons of research in the equating study that one of the most crucial conditions for a successful equating is the anchor will represent content for both the new test form and the old test form. We can study, different equating methodologies, trained post-stratification, IRT observed, IRT true score. But if the content of the anchor is not a good representation of the old and new form, that's kind of, all the methodology itself, like you building a house on the sand. So that's one question I have. And the other one is, as Matthew pointed earlier, I have question about whether the truth here is really the truth. That's, and small sample size is also like related. So I guess that's something we can also consider in the future study. And actually, like a true equating, that's always one of the big question when we run like a equating studies, like what is the truth here? And whether the truth we use in the study can really represent, and then the conclusions based on this truth, like how robust our conclusions can be. So that's my 2 cents. Thank you.
If I could just take the point on the truth, I mean, this may be my explanation of it, but I mean, I think in this instance, we really can be as close as possible to certain that this was the truth, because when we defined our true equating relationship, this used our full test data set. So for effectively before we sampled anything. So and bear in mind that the procedure meant that all of our candidates had actually taken both form X and form Y. So we're using not even just equivalent groups, they're literally the same candidates we're looking at the relationships within a test effectively. And because we're dealing with fairly large samples, we had at least 5,000 students for each test. I think for this, our sense of the true relationship, we can be actually pretty certain is true, but certainly moving away from this very controlled process, yeah, identifying truth would of course be much less clear cut. Do you have anything?
Yeah, I don't want to add to that. I agree with that, and I would also agree that we use the percentile for truth, and I think that's true for us in the sense that what we're really worried about is kind of not truth; it's kind of public confidence. And if two groups of equivalent students have both done a test, and we said on one test 55% have passed, on the same group of students on another test only 45% have passed, that would be terrible for public confidence. That's that people would check, and that is the kind of standard that we're held up to. So I'm happy with X percentile being truth as well as the size of data. Anchor design, I do want to talk about. That's a very good point. Thank you for raising that. Of course, if you have control over the anchor, you do want it to have good representation. I would say that in practice, we can't always control the content of the anchor as much as we'd like. There are often very tight logistical constraints about what the anchor can look like. So it isn't always as representative as you'd like it to be. So in that sense, I think there's some realism into the study that we've done. And I'd also say sometimes a lot of our tests are quite unidimensional. Okay, so they wouldn't strictly pass a unidimensional test, but the items are all broadly measuring the same thing. So whilst I agree with what you're saying, here's what I really think. This is hard to articulate. Sometimes things that test developers think of as being very different constructs within a test psychometrically don't come out as very different constructs, which means that just for the purposes of doing this kind of analysis, a less restricted anchor can be all right. There's a lot of discussion we have around that, but certainly in practice, we did have control. We would want a representative anchor. Somewhat we're constrained by being wanting to do a large study and look over lots of data sets at once. Yeah, but thank you for that point.
I think, and just to pick up on this, this is something that we have in discussion about the work. This is certainly something that, I mean, any follow-up work, maybe something we can start to look into a bit is having more control over the anchor, because there's the content side of it. There's also the anchor difficulty as well, and how that relates to form difficulty. There are various kind of aspects of the anchor it would be nice to have control of. But I would say we probably see that as a follow-on from this effectively. I think if we'd added more conditions still, certainly that would be very challenging to discuss. But it's something we are aware of. So thank you, yeah, for raising that. I should add as well, I see a question in the chat related to this point about test forms we have some control of instead of ability differences. And yeah, related to what I was just saying, certainly test form difficulty. I mean, interestingly, in the context that we operate in, and this is perhaps a little different from those of you in the States may experience test development somewhat differently. We actually don't often have much control over test difficulty beyond expert judgment. Our regulatory environment means we don't pre-test items, for example, and we can't, for certain high-stakes tests at least, use items that have been exposed previously. So each test that we produce is completely new. We actually, in our context, we don't have a great deal of control over test forms. We trust that our test developers are experts in kind of crafting their items. That said, again, this is something that I think it would be nice to look into. We didn't control it, but Tom did look at almost just kind of based on what came out of the random test construction that we undertook. We did look at cases where there was a an appreciable difference in form difficulty.
Or the larger difference in form difficulty. Yeah, but we did look at what happens to our results if we restrict to those cases, and didn't find it having a major effect in terms of which methods perform best. So that's what we can say on that. Yeah, I just want to take the question from the other angle in terms of, we can't control ability differences. It's the very fact that we can't control ability differences that makes it an interesting part of this study. So we can, just by working in the world, very often end up in situations where we have to award grades on the same scale to groups of candidates who've done different exams who are very different levels of ability, and we have to somehow bring it together. So that's why it's of interest, because we can't control it and we have to deal with it. That's why we want to have techniques that can work there. But I better move on to another question.
So just want to make sure I fully, understand the items were not pre-tested when the items are used to assemble a form. So you don't have a really empirical evidence say, okay, my two forms are parallel as much as possible. Of course, SME say the assemble form based on the excuse me, assumption of best judgment, but we really don't know for sure. I want to share. So actually, ETS has done a lot of research on this. Like, okay, when you have test forms, you equate test forms when the items don't have the pre-test stats. Dr. Shelby Haberman, Dr. Neil Durrance, Dr. Sandeep Singhari, they have done a lot of research on this. So you may, search some like ETS research report or JEM articles. Yeah, and that might be, helpful.
Thank you very much.
Mm-hmm. I feel so bad. I have to cut the discussions. I wish this can be continued. We should schedule a longer meeting. But I really appreciate it. I see still there's over 100 audience there. So please feel free to drop in your questions in the chat box. We our leadership has staff to help pass out questions and comments to Tom and Matthew. So it will be addressed through email later. And also here in the slide, you can see their email address. So feel free to drop the questions to them. The purpose of our webinar is not just stop here. We hope to inspire, follow-up discussion and collaborations. And I really appreciate this great talk, Tom and Matthew. Thank you so much. I think everyone enjoyed this webinar just as I have. Thank you again for your time and joining this webinar, and we appreciate your support to the SLE community. Okay.
Thank you very much.
We'll
Thanks
share
for
the
having
slides.
us.
We'll share the slides and the recordings later. Thank you all.
Thank you.
Thank
Thanks,
you.
everyone.
Take care. It's 10